Good morning, afternoon, everyone. Thank you for joining us today for this technical presentation on evaluating large language models. As LLMs continue to advance rapidly and become integrated into critical applications across industries, the need for rigorous, comprehensive evaluation methodologies has never been more important. How can we truly know if a model is performing as intended? How do we measure improvements between model iterations? And perhaps most importantly, how do we evaluate models across the multidimensional space of capabilities they must demonstrate in production environments? Today, I will walk you through the technical frameworks, methodologies, and metrics that represent the current state of the art in LLM evaluation. We will examine everything from academic benchmarks to production-oriented testing protocols, with a particular emphasis on quantitative approaches suitable for rigorous scientific assessment. This presentation is intended for technical practitioners who are implementing or researching evaluation systems. We'll dive deep into the statistical foundations of various metrics, explore automated evaluation pipelines, and discuss cutting-edge research in areas such as LLM as judge methodologies and multi-agent evaluation frameworks. By the end of this session, you should have a comprehensive understanding of how to design evaluation systems that provide meaningful and reproducible insights into model performance across a wide range of capability dimensions. Let's begin with a foundational overview of evaluation objectives. Before diving into specific evaluation methods, let's first establish what we're trying to accomplish with LLM evaluation. As the radar chart on this slide illustrates, there are 6 primary objectives that drive our evaluation methodologies. First, we need to quantify model performance across capability domains. This isn't just about aggregate scores, but about developing nuanced metrics that capture performance across the multi-dimensional space of capabilities that modern LLMs demonstrate. Second, we must establish reproducible benchmarking protocols. The scientific validity of our evaluations depends on methodological rigor and reproducibility. As you can see on our chart, we've made significant progress here, with about 70% coverage of what's needed for truly reproducible evaluation. Third, evaluation should help us identify capability frontiers and limitations. Understanding where models excel and where they struggle informs both research directions and deployment decisions. This area shows the highest coverage on our radar, at approximately 90%. Fourth, we need systems that can detect performance regressions between model versions. As models evolve rapidly, we need automated ways to ensure new iterations don't sacrifice existing capabilities while gaining new ones. Fifth, we must measure alignment with human preferences and values. This dimension goes beyond raw capability metrics to assess how well models reflect human expectations and ethical considerations. As you can see, this remains one of our more challenging areas, with only about 65% coverage. Finally, there's the pragmatic need to optimize computational efficiency. Evaluation frameworks must consider inference time costs, latency, and resource utilization, which is especially critical for models deployed at scale. What's particularly important to note is the unevenness of our coverage across these objectives. While we've made substantial progress in areas like capability identification, we still have significant work to do in alignment measurement and computational efficiency evaluation. This radar chart gives us a starting point for discussing where current evaluation methodologies excel and where they need improvement. Throughout today's presentation, we'll explore how different frameworks address these objectives and where gaps remain in our evaluation approaches. Now that we've established our evaluation objectives, let's explore how we organize the landscape of LLM evaluation methods. This taxonomic framework helps us systematically approach evaluation across 4 fundamental dimensions. First, we have knowledge and factuality assessment. This dimension focuses on measuring how accurately an LLM represents information from its parametric knowledge, what it has learned during training. We examine parametric knowledge accuracy through various benchmarks, quantify hallucination rates using specialized metrics, and evaluate citation and attribution quality, which is increasingly important for models that provide references for their claims. The second dimension is reasoning and inference. Here, we measure logical consistency. Can the model follow chains of reasoning without contradicting itself? We assess multi-step problem-solving capabilities through mathematical and logical reasoning tasks, and we evaluate causal understanding. Can the model distinguish correlation from causation and understand counterfactuals? Third, we have task-specific performance evaluation. This encompasses instruction following fidelity. Does the model precisely execute what it's asked to do? We measure tool use capabilities. How effectively can the model leverage external APIs and functions? And we assess domain adaptation. How well does the model transfer its capabilities to specialized fields like medicine, law, or finance? The fourth dimension is alignment and safety. Here we measure value alignment using preference-based metrics, evaluate adversarial robustness through red teaming, and assess how models handle distributional shifts, maintaining performance and safety as inputs drift from training distributions. This taxonomy not only helps us organize evaluation methods, but also reveals the interconnections between different dimensions. For instance, reasoning failures often lead to factuality problems, and alignment issues can manifest as poor task performance in certain contexts. As we proceed, you'll see how different benchmarks and evaluation techniques map to these dimensions, and how comprehensive evaluation requires coverage across all four. With our taxonomy established, let's examine the major academic evaluation suites that form the foundation of rigorous LLM assessment. Two frameworks in particular stand out for their comprehensive approach: MMLU and HELM. The Massive Multitask Language Understanding Benchmark, or MMLU, offers remarkable breadth with 57 distinct subject categories encompassing over 14,000 multiple-choice questions. These range from elementary mathematics to professional medicine, testing both the breadth and depth of knowledge. What makes MMLU particularly valuable is its standardized methodology. Models are evaluated on exact match accuracy, with clear protocols for zero-shot versus few-shot prompting variations. This allows for controlled comparison across different models and approaches. A crucial technical consideration with MMLU is statistical significance. With diverse categories of varying difficulty, careful analysis is required to determine whether performance differences between models are meaningful or merely statistical noise. The field has developed sophisticated approaches to address this challenge. The Holistic Evaluation of Language Models, or HELM, takes a different approach. Rather than focusing solely on knowledge, HELM evaluates models across 16 carefully designed scenarios targeting different capabilities. What distinguishes HELM is its multidimensional measurement framework. Beyond accuracy, it assesses calibration, how well a model's confidence aligns with correctness, robustness to input variations, fairness across demographic groups, and potential biases in outputs. HELM's methodology emphasizes reproducibility through standardized prompt templates and an automated evaluation pipeline. This infrastructure enables consistent measurement across different research groups and time periods. As you implement your own evaluation systems, these frameworks provide both valuable datasets and methodological patterns. However, remember that they primarily test base model capabilities rather than fine-tune performance on specific tasks. In the next slides, we'll explore more specialized evaluation approaches for specific capability domains. Having established our general benchmarking frameworks, let's examine domain-specific evaluation approaches, starting with mathematical reasoning, a capability that tests both knowledge and multi-step logical thinking. On the left, we have GSM8K, which consists of 8,500 linguistically diverse grade school math word problems. What makes these problems valuable for evaluation is their accessibility. Humans can easily verify solutions, while still challenging LLMs with multi-step reasoning. As you can see in the example, solving even simple problems like calculating remaining pencils requires multiple steps. First calculating the total number of pencils, then the number given away, and finally subtracting to find those remaining. GSM8K introduces 3 critical evaluation metrics: exact match accuracy for final answers, step validation to assess the reasoning process, and error classification to distinguish computational mistakes from deeper reasoning failures. This last metric is particularly valuable because it helps us target model improvements more precisely. On the right, we have the math benchmark, with its 12,500 competition-level problems spanning 5 difficulty levels and 10 subject categories. This benchmark represents a significant step up in complexity, testing advanced topics from algebra and geometry to calculus and number theory. The difficulty gradient is especially valuable, allowing us to precisely identify where models begin to struggle. For instance, most current models perform reasonably well on levels 1 to 2, but show steep performance drops at levels 3 to 4 and near complete failure at level 5. What's particularly interesting about mathematical evaluation is the clarity it provides about model limitations. Unlike some NLP tasks where evaluation can be subjective, mathematics offers unambiguous ground truth and clear reasoning steps. These benchmarks give us insight not just into mathematical abilities specifically, but into how well models can maintain consistent reasoning across multiple steps, a capability with implications for many other domains beyond mathematics. Moving from mathematical reasoning to code generation, we find another domain where evaluation methodologies have rapidly evolved to meet the growing capabilities of LLMs. The HumanEval benchmark has emerged as a standard for assessing code generation. It consists of 164 handwritten programming problems with comprehensive test cases that verify both correctness and functionality. What makes HumanEval particularly valuable is its focus on realistic programming tasks rather than trivial examples. The key metric in code evaluation is pass at K, which captures both deterministic correctness and the probabilistic nature of LLM outputs. This metric measures the probability that at least one correct solution appears when sampling K times from the model. It's a nuanced approach that accounts for variability in model outputs while still rewarding consistent correctness. A critical aspect of HumanEval's methodology is its use of language-specific execution environments that actually run and test the generated code. Unlike text-based metrics that might reward superficially plausible but functionally incorrect code, this execution-based evaluation provides ground truth verification of correctness. For more advanced assessment, benchmarks like code contests and APS draw from competitive programming problems with graduated difficulty levels. These problems require not just syntactic correctness, but algorithmic thinking, optimization, and handling of edge cases. Particularly valuable in these advanced benchmarks is the assessment of test coverage. We analyze how well models anticipate edge conditions and generate appropriate test cases for their own solutions, a metacognitive dimension that reveals deeper understanding of the problem space. What we've learned from code evaluation is that prompt formulation dramatically impacts performance. Our ablation studies show that providing clear context, constraints, and expected formats can improve code generation performance by 15 to 30% on the same model. This highlights the importance of evaluation, not just for comparative benchmarking, but for understanding optimal interfaces to LLM capabilities. Moving beyond specialized capabilities, let's examine how we evaluate an LLM's foundational knowledge and factuality. This dimension is critical because errors in factual knowledge propagate through all other capabilities. The most basic approach contrasts closed book versus RAG testing protocols. In closed book evaluation, we assess what the model has encoded in its parameters through training. RAG evaluation, on the other hand, tests how effectively a model can leverage external knowledge sources. The metrics here extend beyond simple accuracy. We employ precision and recall to measure both retrieval quality and factual correctness. F1 scores provide a balanced measure combining both dimensions. Statistical testing, with methods like Bonferroni correction, helps determine whether performance differences between models are meaningful. A particularly valuable technique is temporal stratification, dividing evaluation datasets into pre-cutoff and post-cutoff knowledge. This approach helps quantify knowledge decay over time and better predict a model's reliability on recent information. Hallucination detection represents another critical facet of factuality assessment. Methods like Self-Check GPT use cross-entropy detection to identify when a model is making unfounded claims. The Chair Metrics framework provides standardized measures for both hallucination rate and severity classification. Attribution analysis is particularly important for citation-enabled models. We measure the number of unsupported claims per response and evaluate citation accuracy through verification against source documents. Perhaps most challenging is establishing inter-annotator agreement for human verification of factuality. The inherent subjectivity of some knowledge domains requires careful calibration of human evaluators to establish reliable ground truth. These factuality metrics not only help us compare models, but also guide targeted improvements. Understanding the specific patterns and domains where hallucinations occur helps us develop more reliable systems for critical applications. Let's move from factual knowledge to reasoning and inference capabilities, a dimension that often distinguishes more advanced LLMs from their predecessors. The most significant methodological advance in this area has been chain-of-thought analysis. Instead of evaluating only final answers, we now validate intermediate reasoning steps using techniques like parse tree generation for natural language reasoning and symbolic verification for mathematical calculations. This approach allows us to distinguish between different error types. We can identify logical coherence failures between steps, computational errors in otherwise sound reasoning chains, and conceptual misunderstandings that permeate the entire solution. These distinctions inform targeted model improvements. A particularly valuable metric is error propagation analysis, which tracks how early mistakes cascade through multi-step reasoning. Models that can recover from early errors demonstrate more robust reasoning capabilities than those where mistakes compound uncontrollably. For complex reasoning assessment, we leverage specialized tasks from the Big Bench reasoning subset with standardized scoring protocols. Syllogistic reasoning evaluations test formal logic capabilities, while counterfactual consistency measurements assess a model's ability to reason within hypothetical frameworks that may contradict reality. The emerging tree of thought methodology extends chain of thought by evaluating not just linear reasoning paths, but also the model's ability to explore multiple solution branches and prune unproductive avenues. By analyzing branching factors and exploration patterns, we gain insight into metacognitive capabilities. These evaluation methods also map to established cognitive frameworks like Bloom's taxonomy, allowing us to situate LLM capabilities within the broader context of cognitive science. This connection helps bridge AI evaluation with human cognitive assessment. What's particularly valuable about reasoning evaluation is how it reveals emergent capabilities. As models scale, we often observe qualitative shifts in reasoning that inform both theoretical understanding and practical applications.